Section 8.1, Systems of Linear Equations in Two Variables. Equations of the form ax plus by equals c are straight lines when graphed. A pair of such equations is called a system of linear equations. The solution to a system of linear equations in two variables is an ordered pair that satisfies both equations in the system. A linear system that has at least one solution is called a consistent system, and a linear system that has no solution is called an inconsistent system. In example 1, we have a system of two equations with two unknowns, and we have an ordered pair that we want to check to see if it's a solution. So we substitute this ordered pair into the first equation, and then we simplify, and that gives us a true statement. So now we'll look at the second equation. We substitute, and we simplify, and we get, again, a true statement. This tells us that our ordered pair satisfies both equations, and therefore it's a solution to the system. In example 2, we have the same system of equations, but now we want to see if this ordered pair is a solution. So we'll start with our first equation, substitute in 7 for x and 6 for y. And when we simplify, we get -4 equals -4, which is true. So that point satisfies the first equation. And now we'll look at the second equation. We substitute 7 in for x, 6 in for y, and that works out to 20 equals 4, which is false. Therefore, the ordered pair fails to satisfy both equations, and so the ordered pair is not a solution of the system. Solving a linear system is the process of finding all ordered pairs x, y that satisfy each equation in the system. We will explore the substitution method and the addition method for solving systems of linear equations. The first step in the substitution method is to solve either one of the equations for one variable in terms of the other variable. Then we'll substitute what we found in step 1 into the other equation, and this will result in an equation with only one variable. We'll solve that equation for that variable, and then we'll take the value that we found in step 3 and back substitute into either of the original equations, and this will give us the other variable. Finally, we'll check our proposed solution in both of the system's given equations. Example 3. Solve by using the substitution method. Step 1. Solve either of the equations for one variable in terms of the other. So if we take the second equation, we can simply transpose the 2x, and we've solved it for y. Step 2 is we'll substitute that value into the other equation. In the other equation, we'll take out y and put in the -2x plus 1 that we found in step 1. Now in step 3, we can solve this equation for x. We distribute the 2, then we combine the x terms, we'll subtract 2 from both sides, and then we divide both sides by -1. This gives us an x value of -2. In step 4, we'll back substitute the value that we found, x is -2, into one of the original equations. Replace x with -2, simplify, add 6 to both sides, and divide both sides by 2. That gives us y equals 5. So our proposed solution is where x is -2 and y is 5. Note that the coordinates of the ordered pair must be in parentheses. In step 5, we will check our proposed solution in both original equations. We substitute and simplify, and that gives us a true statement for the first equation, and we'll do the same in the second, which also results in a true equation. So this verifies our proposed solution, and our solution set is the set containing the ordered pair -2, 5. Note that a solution set must include set braces. Next, we'll look at the addition method for solving a linear system. Step 1 is to rewrite both equations in the form ax plus by equals c. In step 2, we may need to multiply one or both equations by a constant. In step 3, we'll add the two equations, and their sum will eliminate one variable, leaving us with an equation with only one variable. Step 4 is to solve that equation for the remaining variable. And step 5 will back substitute to find the other variable. And finally, step 6 is to check the solution in both of the original equations. Example 4, solve the system using the addition method. Step 1, we rewrite both equations in the form ax plus by equals c, which is already done, so we're ready to move on to step 2. In step 2, we notice that if we add these equations right now, neither variable will be eliminated. So we take a look at the x values, and we notice that if we multiply the bottom equation by -2, we will have opposite coefficients for x. So let's do that. We'll not change the top equation, and we'll multiply the bottom equation by -2. There's the first equation unchanged. And if we multiply 2x by -2, we get -4x. We multiply -3y times the -2, that gives us plus 6y. And finally, the 7 times -2 is -14. Step 3 says to add the equations, and that gives us 11y equals -11. Notice that the x terms canceled out, and now that we have only one variable, we move on to step 4, which is to solve this equation. If we divide both sides by the coefficient of y, we get y equals -1. Now that we have one variable, we can take that value for y and substitute it into either equation. Let's substitute it into the first equation. Substituting that in, we simplify, we add 5 to both sides, and we divide both sides by the coefficient of x. This results in x equals 2. So our proposed solution is the point where x is 2 and y is -1. Step 6 is to check, and this point does check into both original equations. So our solution set is the set containing the ordered pair 2, -1. When we have a system of two linear equations, we can have exactly one ordered pair solution. Graphically, this means that the two lines intersect at a single point. We could have no solution, and graphically this means that the two lines are parallel. Or we could have an infinite number of solutions, and that means that the two lines are identical. Now looking at that graph on the right, it might not look like two lines, but it's because one line is on top of the other line, and that's why there is an infinite number of points of intersection. In example 5, we're going to solve this system of equations, and it'll turn out to have no solution. You don't need to know that going into the problem. The algebraic process will indicate which type of problem this is, whether there's no solution, one solution, or an infinite number of solutions. We'll use the addition method, because if we keep the bottom equation the same, and if we multiply the top equation by 2, then our x terms will line up. 5x times 2 is 10x, and note that those will cancel in a moment when we do our addition. We then multiply the -2y times 2, that's -4y. And finally, we multiply the 4 by 2, and we get 8. We then add the equations, and we end up with a false statement, and therefore, this system is inconsistent and has no solution. The solution set is the empty set. Graphically, this tells us that the lines are parallel and have no point of intersection. Example 6 is a system that has an infinite number of solutions. Again, we don't know that when we begin the problem, so we just start our algebraic process. Because x is already isolated in the first equation, we can use the substitution method. We take our second equation and replace x with its equal, 4y minus 8, and that gives us an equation that has only y. We now solve this equation for y. We distribute, and then we combine the common y terms. Since those y terms drop out, we have -40 equals -40. Since that's a true statement, it indicates that the system has an infinite number of solutions. This solution set can be expressed as follows. Notice the set braces around the entire thing, and then we begin with the point xy. That vertical line means such that, so it's the set of all points xy such that, and then it lists one of the equations. What that means is it's an infinite number of solutions that are all points that are on that line. Therefore, you could have also expressed your answer using the other equation. Graphically, this equation represents the same line twice. So the solution for this system is either of the sets shown here. Suppose that a company produces and sells X units of a product. Its revenue is the money generated by selling X units of the product, and its cost is the total expenses of producing X units of the product. For a company that produces and sells X units of a product, the revenue function is given by R of X equals the price per unit sold times X, the number of units sold. And the cost function is given by C of X equals any fixed costs plus the cost per unit produced times X, the number of units produced. The point of intersection of the graphs of the revenue and cost functions is called the break-even point. Example 7. A company that manufactures running shoes has a fixed cost of $300,000. Additionally, it costs $30 to produce each pair of running shoes. They're sold at $80 per pair. For part A, write the cost function C of producing X pairs of running shoes. We'll use the function C of X. It equals the fixed cost of $300,000 plus the $30 per pair is represented as 30X. For part B, we want to write the revenue function R. R of X will equal 80X. That's $80 times the number of units sold. For part C, we need to find the break-even point and describe what it means. First, let's find it. The break-even point occurs when the graphs of C and R intersect. So we'll find this point by solving the system of linear equations. We'll write it in terms of y, and we'll use the substitution method to solve. We'll take the first equation and replace the y with 80x. We then transpose the 30x to the left and simplify and divide both sides by 50. This gives us x equals 6,000. So now we'll substitute that value into either of the other two equations. So we'll take the simpler one. Substitution gives us a value of 480,000. So the break-even point is where x is 6,000 and y is 480,000. Now that we've determined our break-even point, we need to describe what it means. This means that the company will break even if it produces and sells 6,000 pairs of running shoes. And at this level, the money coming in is equal to the money going out, specifically $480,000.